Welcome back, everybody. In this video, I'm going to be going over a problem that you might see on the GD&T exam. I've put a version of this in the practice exam that I've made. You may also see it in a course if you take a course on GD&T. And the type of question is the distance between two axes on a turned part. So the setup for this kind of question is it's asking the maximum distance between the two axes. So the axis of the 20 millimeter feature and the axis of the 12 millimeter feature. So the 20 millimeter feature is the datum feature A, and the 12 millimeter feature is referencing it at MMB and has a positional tolerance at MMC. So I'll show you the quick way, which I find a little bit prone to error. But what we would do is we would just split it up into the different tolerance. There are different ways we can get tolerance. So in this case, we've got three ways. We've got the baseline tolerance, we've got bonus tolerance, and then we have the additional tolerance from datum shift. So let's look at the datum shift first. The datum feature A is plus minus 0.1. The size is plus minus 0.1. So we would say 0.1 times 2 is equal to 0.2. The baseline positional tolerance is 0.05, and then the tolerance that you can gain from departing from the maximum material condition on the 12 millimeter feature, the bonus tolerance, is 0.2 times 2 is equal to 0.4, and you add that all up and you get 0.65 millimeters of potential tolerance if this were to be made at its all the features were to be made at their smallest condition. So that would be the positional tolerance that the 12 millimeter feature would be allowed, but that's not what the question's asking. This is why I think this is a bit prone to misinterpretation and mistakes doing it this way, is it's asking the maximum distance between the two axes. So what we actually have to do is take that 0.65 and divide it by 2, and we get 0.325 millimeters. And now I will show you the longer way that is a bit more graphical. It's a visual demonstration of it, and I think it's a lot more robust of a way, especially if you're doing the GD&T exam, you have a lot of time to work through it. The approach I prefer to take to this type of problem is to actually draw out the gauge in the part. So I'll draw the gauge, and then I'll make sure to note down what the sizes of each portion of the gauge are. So we know we're looking at the MMB size for datum feature A, which is the largest size, and the size was 20 millimeters plus minus 0.1. So the size is 20.1 on the datum A feature side. And then to inspect the 12 millimeter feature, you would look at the largest size it could be, and then you would add the positional tolerance. So in this case, the datum, or the 12 millimeter feature, the inspection size would be a 12.25 millimeter feature. For drawing the part, I will draw them with an offset axis, and I'll even draw the axis on the part because we're looking, of course, for the furthest distance possible between the two axes. And then we have to think, what material condition will each feature be in to allow for the maximum possible offset between those axes? And the answer is, of course, both at their smallest material condition. So for the datum feature A, the smallest material condition, it was 20 millimeters plus minus 0.1. So therefore it will be a 20 millimeter diameter minus 0.1, which is 19.9. Excuse the terrible writing. And then for the 12 millimeter feature, it was 12 millimeters plus minus 0.2. Therefore the diameter will be 11.8 millimeters. And the final step of this process is to actually just draw extension lines off of all the potential features of interest. For the way that I do it, I like to start with a 0 actually at the gauge center line. It just is easier for me. And then I'll actually make sure I pick a positive and a negative direction, and I will indicate the numbers as such. So in this case, I'll pick up as positive and down as negative. And we'll just start filling in some numbers. So we know that this top and bottom line is each half of the diameter of the gauge size for the datum feature A. And the gauge size for the datum feature A is 20.1. and 20.1 divided by 2 is 10.05. So I will mark down 10.05 on the top and negative 10.05 on the bottom. The gauge size for the 12 millimeter feature is 12.25 millimeters. So this is half of that on each side of the 0, which is 6.125 and negative 6.125. So we know that the diameter of this feature, the size of this feature, is 11.8. So what we'll do is we'll start from this 6.125 location, and we'll say 6.125 plus 11.8, which is 5.675. And I'm cheating, I've already done all the math off to the left here. And we can do the same thing with this, the bottom of the datum feature A gauge, and say from 10.05 we want to go down 19.9. So 10.05 minus 19.9 is negative 9.85. Now we need to do some addition and division for each one of these lines. To get the center line of the 12 millimeter feature, we'll say 5.675 plus negative 6.125, so 5.675 minus 6.125 divided by 2, which is 0.225, and that is negative. And then for the center line of the datum feature A, we'll go 10.05 minus 9.85 divided by 2, which is 0.1. So with all that filled out, we can now just do some simple math to figure out the maximum distance between the two center lines, and we can say 0.1 minus negative 0.225, or 0.1 plus 0.225 is equal to 0.325, which agrees with our earlier calculation, but this is a much more visual way to do it. So that's kind of the two options that I am aware of for doing this type of problem. I find, again, this one, although this seems a lot more complicated, I think because it is much more step-by-step, I find, for me at least, it's a lot less prone to errors. On the GD&T exam, you do get to have a piece of scrap paper and a calculator. So you can do stuff like this, and I was able to ask for more scrap paper if I needed. I'm sure other exam places are similar. Hopefully this was a useful example for anyone studying for the GD&T exam, or for anyone who's just interested in figuring out what are the extremes for a part that they're working with. Have a good one.